What is up, guys? How's it going? Today, I'm going to pretty much talk to you guys about how to parse functions, and it's going to be everything kind of compacted all in one video. So, we're going to be talking about how to parse regular method declarations as well as operator overloads. So, yeah, let's just get right into it. So, I'm going to go here, paste this code at the bottom, and if we look back at the top, methods have a little bit of a different formatting. So, of course, we have our constructor here. Now, let's define a public foo function. Now, if you guys remember, I have a pretty interesting system in my compiler. I have what's called an inferred type system, which means you can either tell the compiler explicitly what you want to process, or you can force the compiler to like figure it out for you. So in this case, what we're doing is we're explicitly saying this foo function has to return this type of var, or maybe it returns like an int. So we have to return, in that case, a int. So let's say we have like a new int, then this is effectively how the function will look. But we can infer the type and can say, this, which the technical term for this is called a inline function declaration. You can basically write out an expression to express what this function or the data that it will return. And it's really nice for like quick and easy functions. So let's just kind of go into it to see how everything looks. All right, so in our method declaration, we're going to have quite a bit of things here. So the first thing you want to do is you're going to want to create your AST method declaration. And then, as usual, we parse our access types here. So we add them, we free up the list. And then after that, we have a check here. So my language supports what's called extension functions. So basically what an extension function is, and I've gone over this before, but just to be really quick, let's say we have an int class, right? So the actual native library int class that's supported by my language. Let's say we wanted to add this foo function to the int class. What you would do is you would say int.foo, denoting that this function is supposed to reside inside of this class. And that effectively acts as an extension function to the class in question. So we'll get into that a little bit later. That's a little bit more of a complex topic, but just for now, you guys are going to want to support processing that. Basically, what we want to do is whenever we process this, we're going to do it a little bit differently. So typically, whenever we have like, I don't know, some type of function or some type of class, it's just like, here's your keyword and here's your identifier denoting like this is the name of this thing, this is the name of the class, or this is the name of the enum or whatever we're processing. But in this case, because we're supporting extension functions, we want to parse a reference pointer. And doing this is really powerful. So here, let me show you another reason why I decided to do that as well and why I think you should follow suit with that. Let's say we have this foo function. Well, obviously we're supporting putting functions inside of other classes without having to physically put the code in the file that the class is declared in. But what it also allows us to do is something really cool, which is like std hashtag. Now, because of the way that our parser is built and the way that our backend is also going to be hooked in together with the parser, the fact that you are using parse reference pointer allows us to also inject functions inside of other standard libraries or other modules, which is really cool because now this foo is effectively a part of the standard library now. And it's really nice. So we'll see a little bit more of that and we'll come to appreciate it when we get to the back end. But for right now, you don't really need to worry too much about why it's but for right now, you don't really need to worry too much about it. Just know that you need to add your reference pointer. Now, if we have operator here in our reference pointer, if you remember, we can process that. We can say operator equals whatever. We don't want to do that. Now, when we're processing this, if you notice here, I have a check for if the current token or the next token is equal to operator. And the reason why is because parse reference pointer supports the operator equals thing. If you guys remember, we have something like operator equals, it supports processing a reference pointer as that. We don't want to allow the user to do that for here because operator overloads have slightly a bit of a different format. All right, so I made some changes. And after you parse a reference pointer, then you're going to want to do a check. Now, this is where it gets into personal taste. There's not really a good reason for this. We're going to get to it a little bit more when we go into the back end. But basically, in short, I'm not allowing extension functions on operator overloads. Now, a big reason for that was because extension functions kind of came at a much later date in terms of compiler development, and operator overloads were still kind of iffy. They still weren't really supported in the language. So I've kind of been put in a weird situation where kind of how my compiler is processing things. I don't want things to be messy. I want things to be clean, and I have a very good system put in place. So I didn't want to tack on more complexity by also supporting operator overloads as a way to use extension functions. So you basically can't say int dot operator equals. So we're not going to be doing that. If the user wants to implement a operator overload onto a class, then they're going to have to use class mutations. But yeah, that's, like I said, it's just a small thing. You guys can do it if you want. And I'll explain later on in the tutorial series on how to support extension functions with operator overloads. But yeah, that for right now, this is just kind of what I have. First thing you want to do is, of course, you want to parse your arglist. So you want to parse your utype arglist. That's going to represent the arguments of the actual method. Once you do that, now here's where it gets into the logic to figure out what you're going to be processing when you're processing this function. This is important because when we get to the back end, this is going to help the type system basically figure out, do we have to infer the type of this function, or can we just kind of figure it out explicitly? So this kind of helps out the back end. So the first thing you want to do is check to see if the next token is equal to a colon. So if that's the case, well, we're going to immediately expect a type immediately after the colon. So we're going to parse a method return type here. Now let's kind of go into that. And what that does, it basically checks to see if the next token is a colon. Now we've already done that here, but we're just peeking here because we have to figure out the formatting. It kind of does it a second time here, but this function is also reused in other spots. So that's kind of why it does this check. But basically, we want to create a branch called AST method return type. We want to advance one character to get to this colon token. And then we want to peek forward one. So if it's going to be equal to nil, that means that our function is basically returning nothing. This is our void version in our language. So nil basically means nothing. After that, you can advance, and so you can consume the nil token here by advancing and then adding it to your branch. This is important. You definitely want to add this because you want to tell the backend that this is what the function is returning. Otherwise, you just parse a utype, which we all know what that is. And yeah, so that's how you parse a method return type. Pretty straightforward. So the next thing we do is we check the next token to see if it's equal to an equal sign. So even though you're explicitly specifying that, okay, here's the type of the function, you can still have an inline function declaration. Our compiler and our type system is going to be smart enough to figure all this information out perfectly. So we want to allow the user to be able to do whatever they want. So we just check to see if the next token is equals. If so, we expect that character. Be sure to please add this token to the branch. That's very important. Once you do that, you want to parse an expression. Now, to be honest, I'm really trying to delay this function as much as humanly possible. I'm still working on parsing expressions, and I got some stuff that I got to do on the back end that's heavily dependent on this function. So there have been loads of things that have been changing in here. So for right now, just create the function parse expression and create an AST expression enum. We'll get into parsing expressions a little later, but yeah. After that, you want to expect your semicolon. You do not need to add that. So that's the case where we have like an equal sign. So we have our type, our colon, our type, our equals, and then here's our expression. So after that, the next thing you're going to want to do is check to see if the token or the next token is a semicolon. So we've already processed the situation where we have an equal sign and we process a inline function declaration. Now we're going to process a delegate declaration. Now we've gone over delegates before, but here's basically the formatting. So you have your foo, your defined foo, you have your args, and then you have your semicolon. This is going to denote, especially on the back end, that the user has to implement this function if they decide to inherit this list class. So that's the concept of delegates. So just change the AST type of the branch to AST Delegate Declaration. Otherwise, we just parse a block. So, and again, this is all under the colon assumption. So this is all assuming that we have, a colon, some type, and then we can do something like that. So once we do that, we have this infer here. So now we have the infer symbol. So what that's going to be is that's going to be this symbol. And the infer symbol is basically going to say, all right, well, if it's an infer symbol, immediately process an expression, or of course, consume the token. And again, make sure you add the token. This is very important. Consume an expression and then consume a semicolon at the end of this. So there's that. So that's pretty straightforward. And then so let's say have like 0 here. So you can do something like that. And that's how an inferred function type will be. This is really nice. I really like this syntax. It's super clean and it's really nice. So yep, that's pretty much how you do an infer. After that, you have a semicolon. So now, if you guys remember, we had a type here, and I also had a semicolon immediately after that. Well, this is still considered a delegate function, but hey, sometimes you might just return nothing, right? You can specifically say you want to return nil, or you can just not put anything because you're not required to write out the type of the function that it's returning. If you don't want to return anything, you don't have to specify that you don't want to return anything. So, and if all of this fails, right, like if we process the colon, if we process the infer type, if we process the semicolon, and we again, I don't think I mentioned this, but you consume the semicolon token and then you change the type here as well, it's pretty much the same code that we saw up here. But if we processed all of this code and we still don't know what the heck's going on, then we're just going to parse a block. And that's like our last resort. And if there's something going on there, then obviously the user has made an error. We just kind of complain about it. So let's kind of see all of the different forms. And we're going to see this more so on the backend side of our compiler. But let's just kind of do a quick run through to see how everything looks. So the first thing I'm going to be doing is the delegate syntax right here, where we just have a semicolon and a delegate declaration. So yeah, let's go back here. All right, so we have a AST delegate declaration. We have our access types. We have our reference pointer, which is just foo for now. And then we have our utype arglist of whatever. And obviously there's nothing in here because we don't have any parameters. If there was, we would have utypes in here. But this is the basic formatting. You don't need any extra information. You just need the type of the AST that we can check on the backend side, so that way we can know how to process this information. So let's look at the next one. So next we're going to look at an infer. I am going to put an expression here, but we'll go over expressions later. So I'm going to say 0. So foo is equal to 0. All right, so we have our foo. It's a method declaration. We process our access types. We have our reference pointer of foo. We have our empty utype arglist, and then we have our expression. So we have our expression. It's a primary expression. It's a literal expression. Then we have our literal value of 0. So that's just kind of the basic formatting for a inline method declaration. All right, let's kind of go up. Now let's look at a case where we have a colon. So we have our type here, and then we have our semicolon. All right, so I'm going to recompile here and let's just kind of see how this looks. So we have our delegate declaration again. We have our access types, our reference pointer, our empty args, and then we have our AST method return type. So we haven't seen this one yet. So it's basically just consists of a utype, and our utype is type. Now the compiler thinks that this is a class. It doesn't think that this is a native type, which is fine. So that's why it's a utype type identifier reference pointer of type. But let's say I put nil here, and let's kind of see what happens then. So if I put nil here, you can see that we have a method return type of nil. It's very simple. So it just literally plops the token in there. So on the back end, we'll just have to check for this token. And if this token is here, then we process that. Otherwise, we try to figure out what the type is. All right, so the final thing I can do is equals. So let's do this. So I'm going to say type here and equals 0. So it's going to basically be this. We've kind of already seen this. It's basically just like infer, except that this time it's going to have the return type. So we have our method declaration function. We have an equals, so we have the equals token here, very important. We have our access type public. We have our reference pointer of foo, our empty args. We have our return type here. Our return type is going to be type, and as you can see here, of course, it's a U type of type. After that, we have our expression. As we've seen before, it's a primary expression. It's a literal expression of 0. So yeah, that's pretty much how we process this code. Hopefully that made sense. And let's kind of look at how we process operator overloads. Operator overloads, like I said, it was kind of an afterthought when it came to processing things in my language. Um, they're not a relatively new concept, but in terms of where I am in development of my compiler, they're usually pretty new. I usually try to wait to process operator overloads because they usually add an extra layer of complexity to your actual compiler because you actually have to do loads of checks and various different things and add tons of rules to make sure that you're processing operator overloads in the right spots and then not processing them in other spots. So just kind of keep that in mind. But this code is basically exactly the same as the code we just saw. It's literally no different except for AST underscore operator declaration. And of course, instead of parsing a reference pointer, here we're expecting the token operator, and then we are processing we're expecting an override operator. But outside of that, I mean, to be honest, this is exactly the same function. So I don't think I have to go over this, and I'm not really going to, if I take it back, I'm not actually going to show you guys the code output because we literally just saw it. So just literally create this function, parse operator declaration, and have this code here. Now, if I were integrating this a lot better, what I would probably do is I would probably delete this function altogether and just merge the code of this inside of the parse method declaration function. So I wouldn't have two of these because they're basically the same. I would just kind of merge it, figure out if the reference pointer, like if the override operator is the last token that we processed. As you know, if you process it at the beginning, the override operator is going to be the last token you process. And if you process it at any point while you're processing a reference pointer, it will also be the last token you process. So we can basically pretty much guarantee that even if we have an extension function that is an extension function for an override operator that's supposed to be placed in a different class, we can just basically set the AST here to AST underscore override operator. That's what I would do if I didn't want to create that unnecessary second function, but yeah. So that's going to be it for today, guys. That was a lot. Hopefully that made sense for you guys. As usual, if you guys have any questions, definitely write them in the comment section below. I know I threw a lot of information at you today, and I went pretty quickly. So if I skipped over anything or if I maybe missed something, definitely point that out. And I can hopefully put it in another video or maybe get to it in the comment section. And as per usual, I'm going to go over to my Github repository. If you guys would love to help out the channel, definitely head over to andrewdevcd/sharp. This is going to be my GitHub repository where I do pretty much all of my development for the language. And when you head over there, definitely watch, start, and fork this repository. That's going to give this language a ton of more visibility and let other developers know this language exists. Also, if you're pretty curious about what I'm doing in the day-to-day with the language, definitely head over to the remastered branch. This is going to be the main branch that I'm doing all of my active development on a daily to weekly basis. And you can check out the commits here. I write some pretty wordy commits, so you can kind of see and get an idea of what I've been up to in each of the commits to kind of see maybe things that I'm adding or maybe bug fixes that I've put in. Or if you're curious about maybe stuff that I've done in the past or maybe things that I'm looking to add into the future for this language, you can head over to the doc folder. And in the docs folder, I'm going to have two main files that you can look at. You can check out the changeless file. That's going to be pretty much everything I've done to the language in the past. And then you can also check out the roadmap file, which is going to pretty much contain everything that I've done in the language thus far, whether it's be in the past or stuff that I'm looking to add in the future. It also has checkboxes in there, so you can actually see the things that I've actually finished in the language currently. So this one's a pretty interesting one, so I would definitely recommend you check that one out. But yeah, so that's going to be it for today, guys. Hopefully you enjoyed the video. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. Until next time, I'll see you guys later.